Okay, 11.4, last section of chapter 11. We're going to talk about the introduction to derivatives. So this is kind of an introduction to calculus a little bit. Find the slopes of the equations with tangent lines. Find the derivative of a function. Find the average and instantaneous rates of change, and find an instantaneous velocity. The average rate of change between any 2 points of a graph of a function is the slope of the line containing the 2 points. It's called the secant line. So here's the slope of between 2 points. It's just a secant line. Following the same way as before, change of y over change of x. The figure shows how the secant line between points in Q changes as h gets closer and closer to 0. The limit positioning of secant line is called the tangent line to the graph of f at point A, f of a. So in other words, you start here, and it gets smaller, smaller. So it gets closer and closer to a tangent line. And a tangent line touches the graph at one spot only. The slope of the tangent line to the graph of a function y equals f of x at a f of a is given by this. The slope of the tangent line is equal to limit as h goes to 0 of f of a plus h minus f of a over h, provided that a limit exists, and the limit also describes the slope of the graph at f and the instantaneous rate of change of f with respect to x at a. So this is my slope of a tangent line equation as h goes to 0. Find the slope of the tangent line of the graph of f of x equals this at 4 and 12. At the point 4 and 12, a is 4. So a is 4 at point 4 and 12. So we're going to use this formula. So we're going to plug in f of 4 plus h minus f of 4 over h. So we plug in, now this is the toughest part, we're going to plug in 4 plus h into x squared and 4 plus h into x minus 4 squared minus 4 over h. Simplifying down the limit of this, so we get h squared plus 7h over 4h, factor out of h on top. So we have this equation. So we plugged in these values into here, and now we have the h on top. We factor out the h, cancel them off, and now we're going to plug in 0 for h. So we're going to get a limit of 7. So the slope of that tangent line is 7. So find the slope-intercept equation of the tangent line of f of x equals x squared root of x at 1, 1. So kind of the same thing. We begin by finding the slope of a tangent line to the graph at 1, 1. So the measure of f of h, a plus h minus f of a over h, 1 plus h minus f of 1 over h. So we got the square root equation. So it's square root of 1 plus h minus square root of 1, which is 1, over h. Now on this one, what we need to do here, we need to multiply the top and bottom by the conjugate of the top. Because right now, if we plug in 0, we're going to have 0 on the top and 0 on the bottom. And that's not a good thing. So if we multiply top and bottom by the conjugate, so really it's going to be one of those things we talked about before, is rationalizing, but we're going to rationalize the numerator. So we're going to have 1 plus h minus 1 over h times this. 1 plus 1 is 0, so we have h, and the h's will cancel off on top and bottom. What happens here, these two, the 1 and the negative 1 will cancel off. H goes into here, 1. So we have 1 on top, and this is the bottom. Now if we plug it in, we're going to get a limiting factor of 1/2. So we found our slope. Our slope is 1/2, our point is 1, 1. So we're going to go to the next step now. Our next step is to write the equation. So therefore, the tangent line goes through 1, 1 with a slope of 1/2. We're going to use the point slope equation form. We plug in this formula, 1/2, plug in 0.11. And if we simplify this down, we're going to get y minus 1 equals 1/2 x minus 1. Add 1. Here's our point slope equation that we're looking for when we do this. Now, this formula that we talked about finding the slope at a point is many names for it. Let y equal f of x denote a function f, the derivative of f at x, denoted by f prime of x, is defined by the same function, but instead of using a, use x, provided that the limit exists. The derivative of a function f gives the slope of f at any value of x in the domain of f prime. Now we'll be careful on this. I mean, we're going to mainly be doing basic derivatives to start with, but there's more to a derivative than this, but we have to start with the basics as we go through this. Find the derivative of this. So basically, that is find f prime of x. We're going to do that f of x plus h minus f of x over h, limit as h goes to 0. So if we look at this formula, we're going to go like this and say, okay, we're going to plug in x plus h into our equation, and x plus h here. So we get x plus h squared minus 5 times x plus h minus x squared plus 5x over h. Foiling this out, minus 5x minus 5h minus x squared. Now you notice here, they made a mistake. And I think they calculated themselves to that next step. But right here, this x comes through the parentheses. So this should have been, if they were doing the math right, bringing this minus through, that should have been plus 5x, because they did it right, because those two cancel off because they don't have it there. The x squares cancel off. One thing you'll notice that this back term should always cancel off. So we have this. Factor out a h on top. H's will cancel off. Now if we plug in 0 in here, we get the limit as h goes to 0 of 2x plus h going through here. 2x plus 5, I mean. Which is neat because it says, if on this function, if I ever want to find a slope of a point, slope at any point of that function, that's all I need to do is take the x coordinate and plug it into this equation, and it'll tell me what the slope at that point is. That's how powerful a derivative function is. Now it says find the slope of the tangent line to the graph of this at x equals 1. Well, we already know the equation. We know it's 2x minus 5 from the previous problem. So therefore, now if I want to find the slope of the tangent line, I plug in -1. If I plug in a -1, I get -2 minus 5 is a -7. So at a -1, my slope is a -7. At 3, plug in 3 here. I'm going to get 6 minus 5, which is 1. So at 3, my slope is 1. The average rate of change of f from x equals a to x equals a plus h is given by the difference quotient. The instantaneous rate of change of f with respect to x at a is the derivative of f. So instantaneous is always the derivative. That's the limit. Average is just taking the 2 points and averaging. A function's f of x equals x cubed describes the volume of a cube f of x in cubic inches, whose length, width, and height measure x inches. If x is changing, find the average rate of change of volume with respect to x as x changes from 4 to 4.1. So, in other words, h is 0.01. If we follow the formula here, average rate of change, f of a plus h minus f of a over h. A plus h, 4 plus 0.1, minus f of 4 over 0.1, 4.1 cubed, minus 4 cubed over 0.1, which is 49.21. So the average rate of change is 49.21. This describes the volume of the cube, f of x in cubic inches. If x is changing, find the instantaneous rate of change of the volume with respect to x at the moment when x equals 4. So now, instantaneous, we need to take the limit. So we get the limit as f of x plus h minus f of x over h, which is equal to the x plus h cubed, because we're doing the cube rule. We're going to cube that out. That's going to take a little time to FOIL. Bring that up here. So what they did is they took this and cubed it out and got that whole thing minus x cubed. So those will cancel off. So we get that on top over h. Factor out of h. Those will cancel off. So we're going to get this 0. So 0 and 0. So our answer, this is timesing. Our answer is 3x squared for our equation. Now, instantaneous rate of change, if find the instantaneous with respect to x, and with x is 4, so I think we need a little more answer here. So the instantaneous rate of change at 4, they didn't put in here, so what we would do is plug in 4 here. We get 16 times 4. 16 times 3 is 48. So at 4, our instantaneous rate of change is 48. Suppose that a function expresses the object's position as a t in terms of time. The instantaneous velocity of an object at time t equals a is this. Again, it's the derivative formula. Instantaneous velocity at time a is called the velocity at time a. So pretty much the derivative again. A ball is thrown straight up in the air from the ground with initial velocity 96 feet per second. Velocity's function is this. Describes the ball high above the ground as a t in feet, t seconds after it's thrown. What is its instantaneous velocity after the ball is t seconds in the air? Instantaneous velocity is given by the derivative of the function that expresses the object's position as a t in terms of t. So, the instantaneous velocity of a ball 4 seconds is s prime of 4. So it's a derivative at 4. So we got a little work to do. So what we need to do is take the derivative and plug in 4. S of a and S of a plus h minus S of a over h. So we plug in a plus h and h, FOIL everything off, cancel off, plug in the limit as h goes to 0. We're going to get a negative 32a. Notice right here, negative 32 plus 0 plus 96 because we're plugging in 0 for h. So we're just going to kind of go back through here. We're plugging a plus h in twice, a in twice, divided by h. FOIL it out, get our answer. Plug in that, you get negative 32 plus 96. Now at 4 seconds, we have to plug in a little bit more here. We should plug in 4 seconds into this equation to figure out what is the instantaneous velocity at 4 seconds. So therefore, we would plug in 4 here. So we get negative 32 times 4 plus 96, which is negative 128 plus 96, which is a negative 32. So this instantaneous velocity is a negative 32 feet per second. So not too hard, we're just kind of doing the derivatives as we go through. Thank you.